Imagine for a second just dropping your laptop straight into a swimming pool.
Oh.
Right. And suddenly realizing you just permanently orphaned your entire company's cloud infrastructure.
That is the ultimate nightmare scenario right there.
It really is. I
Yeah.
mean, you've got live databases, heavily trafficked load balancers, thousands of virtual machines just spinning out there in the real world. But your localized map to actually control them, that is currently sitting at the bottom of the deep end.
Yeah, that is not a good day at the office.
No, definitely not. So welcome to the deep dive. Today, we are heading straight into the highly intricate world of Terraform backends and state migration.
We really are. And, we're pulling our insights directly from the official HashiCorp Terraform Associate 003 exam documentation today.
Which is super detailed.
Oh, absolutely. But the stakes here, they extend way beyond just getting a good certification score. Because the state file is the absolute, undisputed source of truth for your infrastructure.
It really is the master blueprint.
Exactly. If you lose synchronization between your code and that state file, you are essentially flying completely blind.
So our mission today is to equip you, the listener, with the exact knowledge you need to navigate all these mechanisms safely.
Definitely.
Whether you are studying right now to ace those back-end questions on your certification exam, or maybe you're a team lead who is terrified of losing production data because your infrastructure state is currently just marooned on one single developer's machine.
Which happens way more often than people want to admit.
Oh, for sure. You need to migrate it to a shared team environment, and you need to do it without losing a single byte of data.
Right. And to do that securely, we really have to deeply understand the architecture of the backend itself.
Right.
Because when most engineers first start learning Terraform, they just run Terraform init and apply in a local folder.
Yeah, just right there on their desktop.
Exactly. And Terraform handles everything right there.
Okay, let's unpack this, because the source material uses this concept of a home address, right?
Yes, that's a great way to look at it.
When you run Terraform locally, just out of the box, it creates this massive, highly sensitive JSON file right in your working directory.
Which is pretty risky.
It's basically the equivalent of leaving the master blueprint and the physical keys to your entire production environment, just sitting on a public park bench.
Yeah, literally anyone with file system access can just walk up and view plaintext database passwords.
Right. Passwords, mapped attributes, dependency graphs, internal binding IDs, all of it.
Just sitting there in plain text.
So moving to a remote backend puts that master blueprint into a heavily fortified vault with strict logging and multiple locks.
Exactly.
But aside from just acting as a secure storage locker, the backend actually dictates the execution flow, right?
It does. Backends fundamentally handle two distinct responsibilities in Terraform's architecture. First, as you mentioned, they securely store the state.
Right, the vault.
Right. They determine exactly where that critical JSON file lives. But second, they optionally determine where the core operations actually run.
Like the resource graph calculations and all that.
Exactly. So for the exam, and really just for enterprise architecture in general, you absolutely must distinguish between the two specific classifications of backend.
Which are standard and enhanced, right?
You got it. Standard and enhanced.
Okay, so let's draw the line between those two. A standard backend, like AWS S3 or Azure Blob Storage or Google Cloud Storage, that acts strictly as a storage vault.
Just a vault. Yeah.
So when I configure an S3 backend, my state file is locked safely in an AWS bucket, but my local laptop is still sweating.
Oh, yeah, your fan is definitely spinning.
Right, because my machine's CPU is calculating the dependency graphs, doing the state refresh, pushing all those API calls out to the cloud provider.
And that is the defining limitation of a standard backend. The storage is centralized and secure, sure, but the heavy lifting of the Terraform plan and Terraform apply commands, that is entirely localized to whoever is running the terminal.
Just burning up their local hardware.
Exactly. And then you have enhanced backends, which HashiCorp defines to include the local backend itself, technically.
Wait, really? Local is enhanced?
Well, functionally, yes, because it handles both storage and compute locally. But more importantly for teams, enhanced backends include Terraform Cloud and Terraform Enterprise.
Oh, okay. So an enhanced backend shifts the compute. It's like renting out a massive, centralized, remote data center to do the complex math for you rather than just melting your local CPU.
That's a perfect analogy.
You aren't just storing your state in the vault. You're actually sending the instructions to a dedicated execution environment that handles all the processing natively.
And that execution shift is critical for teams.
Why is that?
Because it completely eliminates the classic "it worked on my machine" discrepancy.
Oh, I hate that phrase so much.
We all do. With an enhanced backend, the environment where the plan is executed is identical every single time. It doesn't matter what operating system or local dependencies the engineer happens to have on their personal device.
Okay, so we know we need this remote vault, whether it's standard or enhanced. But as an engineer writing code, how do I actually hand Terraform the map to find this vault without exposing the access credentials to everyone on GitHub?
That is the million-dollar question.
Because as a developer who loves keeping code DRY, don't repeat yourself, my immediate instinct is just to use variables.
Of course.
Right. Like I want to define var.backend access key or var.bucket name right inside the Terraform configuration block. That way I'm not hard coding my sensitive cloud parameters in plain text.
It makes total sense logically.
It seems like the most standard way to write infrastructure as code.
It does. But what's fascinating here is the strict internal architecture of Terraform's initialization phase.
Uh-oh, there's a catch.
A huge one. Using variables inside the backend block is the classic trap that trips up almost every single candidate on the exam.
Really?
Yes, and it frustrates countless new developers. You absolutely cannot use variables there, and the reason comes down to a really strict order of operations.
Oh, I see. It's a chicken-egg problem, isn't it?
Basically, yeah.
Terraform has to evaluate the backend block during the Terraform init phase, which is long before it even processes the variables during the plan or apply phases.
Precisely. Just think about the physical mechanics of what might be happening. Your variables, which might be stored in a terraform.tfars file, those might actually be hosted in the remote workspace that the backend is trying to connect to.
Oh, wow.
Right. So if Terraform needs to read the backend block to go find the variables, it inherently cannot use those variables to define the backend block itself.
That creates a complete paradox.
It does. Therefore, you cannot interpolate variables, and you cannot reference data sources inside a backend configuration block. HashiCorp restricts it entirely.
Okay, here's where it gets really interesting. Because I categorically refuse to hardcode my AWS access keys or even my dynamic bucket paths directly into a plain text configuration file.
Nor should you.
If I commit that to version control, my security team is going to automatically flag the repository and just revoke my access on the spot.
As they should.
Exactly. So if variables are strictly prohibited during the init phase, HashiCorp must have built a workaround that doesn't completely compromise security.
They did. They engineered a mechanism specifically to solve this dilemma, and it's called partial configuration.
Partial configuration. Okay.
Yeah. You leave the sensitive arguments, like your access keys, your secret tokens, specific dynamic state paths. You leave all of that completely out of your main Terraform block.
Wait, really? Just leave it out entirely?
Yep. You might just define backend, quote, S3, unquote, and leave the block entirely empty.
So instead of taping the combination to the front of the vault, you basically keep the vault's address in the main file, but hand over the combination separately when you actually walk up to the door.
That is exactly how it works. You provide those missing pieces strictly at runtime.
Okay, how do we actually do that?
Most engineering teams accomplish this using the -backend -config flag when they run the Terraform init command.
Ah, okay. I've seen a couple of ways to handle that flag. You can pass a separate file, right? Like a secrets.tf backend file that contains the credentials.
Yes, you can.
And then you just aggressively add that file to your .gitignore so it never accidentally touches your repository.
Exactly. That's a very common pattern.
Or, I guess if you're running in an automated CI/CD pipeline, the pipeline runner can just inject the configuration as key value pairs directly into the command line. Like -backend -config equals, quote, bucket equals my production state, quote.
Both of those methods are perfect. They both satisfy Terraform's strict initialization rules without violating your organization's security posture.
That makes a lot of sense.
By splitting the configuration, your main TF files remain clean and completely free of secrets, while the localized runtime environment safely supplies the missing authentication layer.
So what does this all mean for that nervous engineer we talked about earlier?
Right, the one with the laptop.
Yeah, the one who has the entire production state locked inside a JSON file on their local hard drive.
Yeah.
Because we have our S3 vault configured securely now using partial configuration.
Yes, we do.
We bypass the variable trap. But the actual valuables, the mapped IDs and the dependency graphs, they are still sitting on their local hard drive.
They are.
How do they physically move that localized state up to the cloud without destroying everything and dropping the database?
The transition relies on a very specific command flag during initialization. You have to run terraform init-migrate-state.
Okay, because just a standard Terraform init won't actually move the data, will it?
No, it won't. And that's a huge trap. If you change your backend configuration block from local to an S3 bucket and you
Mm,
simply run a standard Terraform init, Terraform detects that the backend has changed.
okay.
However, it assumes you are starting completely fresh.
Oh, no.
Yeah. It will initialize the new remote backend, but it will leave your existing local state file sitting right where it is. So your new remote vol will be fully functional but completely empty.
Which creates a catastrophic scenario.
Very much so.
Because if you have an empty remote state file and you run Terraform apply, Terraform checks the remote vault, sees 0 resources, looks at your code, and attempts to provision every single piece of infrastructure from scratch.
Right. It thinks nothing exists yet.
You will instantly hit massive constraint errors as the cloud provider rejects duplicate VPCs and database names that already exist in reality.
Exactly. So by explicitly adding the -migrate-state flag, you are actively instructing Terraform's internal engine to take the existing local state file, copy its contents up to the new remote vault, update the lineage and serial numbers, and remap all the internal pointers.
So your future operations actually target the remote file.
Precisely. And the source material actually notes there is a mandatory interactive prompt during this process.
Oh, really? Like a confirmation?
Yes. Terraform will literally pause your terminal and require you to type yes to confirm that you actually want to copy the state to the new backend.
That makes sense. It's a built-in safety net to prevent automated scripts from accidentally overwriting remote states.
Exactly. And, this raises an important question about operational safety and really why we migrate away from local state in the first place.
Right. Why bother if it's working for me?
Well, the local backend is perfectly acceptable for a single user working on an isolated sandbox project. When you run a command like apply locally, Terraform creates a hidden file called .terraform.tfstate.lock.info.
Oh, I rely on that file constantly. It's a temporary lock.
Exactly.
It prevents me from accidentally opening 2 terminal windows and
What?
trying to run 2 overlapping Terraform apply commands simultaneously.
Because if you did that,
It would create a race condition and just irreparably corrupt the JSON file. It acts like a do not disturb sign for my own operating system.
it does. But consider the limitation here. That .lock.info file only exists on your specific hard drive.
Well,
If you and I are both working on the same project, and we decide to just share a state file over a network drive, or like a synced Dropbox folder without using a true remote backend, my laptop has absolutely no awareness that your laptop has created a local lock file.
that is terrifying.
We could both hit apply simultaneously. Terraform would try to write to the state file at the exact same millisecond, and we would instantly corrupt the shared state.
Because the local lock is only locking my local kitchen table. It doesn't lock the shared vault.
Exact.
To prevent my team from stepping on each other's toes, we need a mechanism that locks the state remotely.
Which is exactly what a backend like S3 provides, provided you pair it with DynamoDB.
Let's dig into the mechanics of that DynamoDB lock because it's honestly a brilliant piece of engineering. S3 by itself doesn't have a native locking mechanism for Terraform, right?
No, it doesn't. S3 just stores objects.
So we configure Terraform to point to a specific Amazon DynamoDB table. When I run an apply, Terraform instantly writes a tiny record into that NoSQL table containing a unique session ID and an operation timestamp.
Right. And while your operation is running, that record just sits there in DynamoDB.
Just holding the door shut.
Basically, if I try to run an apply from my laptop 5 seconds later, my Terraform client reaches out to that same DynamoDB table, sees your active lock ID, and immediately halts my execution with an error stating that another operation is currently in progress.
Wow. It guarantees mathematically that only one person or one CI/CD pipeline can alter cloud reality at any given time.
It really is the ultimate peace of mind for a platform engineering team. Moving from local state to a centralized, locked, remote backend is a mandatory architectural evolution for any scaling organization.
But let's look at the next stage of that evolution. I'd say I just spent all this effort, right? I used migrate-state. I implemented partial configuration via my CI/CD pipeline, and I got everything humming along perfectly using S3 and DynamoDB as my standard backend.
Sounds like a great setup.
It is. So why should I care about changing my configuration block to something entirely different? If the S3 vault is secure and locked, why touch a system that works?
Well, if we connect this to the bigger picture, it's about operational efficiency and minimizing your attack surface. Historically, if you wanted to migrate away from S3 and utilize Terraform Cloud to take advantage of its centralized run environments, you would use a backend block specifically named Remote.
Oh, yeah, I remember the remote backend block.
Yeah.
You would nest it inside the Terraform configuration, just like the S3 backend.
Exactly. But HashiCorp has fundamentally evolved this pattern. The modern, explicitly recommended approach for integrating with Terraform Cloud completely abandons the standard backend syntax.
Oh, really?
Yeah. You don't use backend quote remote unquote or backend quote cloud unquote. Instead, you use a completely new top-level configuration block simply called cloud.
So the syntax is literally just Terraform curly brace, cloud curly brace. It bypasses the traditional backend mapping entirely.
It completely replaces the backend block for Terraform Cloud users because the platform does so much more than just store state. By migrating your code to use the cloud block, you are deeply integrating with HashiCorp's managed infrastructure.
Which ties directly back to our earlier discussion about enhanced backends.
Yes, exactly.
Because by adopting the cloud block, I'm fully shifting the execution environment. I am outsourcing the heavy compute-intensive planning, the API credential management, and the resource calculations completely off my local laptop and into the cloud.
You're offloading all of it.
My laptop essentially just becomes a walkie-talkie, sending the initial signal to start the automated construction crew.
That is a brilliant way to put it. Furthermore, it natively handles workspace management, centralized variable storage, and RDAC, role-based access control, without requiring you to stitch together S3 buckets, DynamoDB tables, and custom IAM policies.
Oh, so it consolidates the security perimeter.
Exactly. It simplifies everything.
That is a massive architectural upgrade that reduces operational overhead.
Right.
Well, we've heavily analyzed the storage vaults, the initialization traps, the migration mechanisms, and the modern cloud block integration.
We've covered a lot of ground.
We really have. Let's see how this actually applies in the real world and how it translates to the Terraform Associate 003 exam.
Let's do it.
I was actually looking over a pull request from a junior engineer last week that perfectly highlights these concepts. They were trying to be super clever and keep their code modular, so they defined a variable called var.productionBucketName and placed it directly inside their S3 backend block. I had to reject the PR immediately. If they had attempted to run Terraform init on that branch, their terminal would have just exploded with syntax errors.
Oh, absolutely. The initialization would fail immediately before it even attempted to connect to AWS.
Because variables are fundamentally incompatible with the initialization phase.
Exactly. Terraform must load the backend configuration and establish the connection to the state file before it can parse the dependency graph to evaluate variables.
No.
If an engineer needs dynamic inputs for their backend, like injecting different bucket names for different environments, they must leave the arguments out of the main block and use partial configuration with the -backend-config flag.
And the exam tests that.
The exam will repeatedly test your understanding of this specific restriction.
Good to know. Okay, another situation I saw recently involved a platform team managing some incredibly massive monolithic infrastructure. They had hundreds of complex modules just chained together.
That sounds heavy.
It was. Whenever they ran a Terraform apply, their local laptops completely froze up. The cooling fans sounded like jet engines because the CPU and memory were totally maxed out, just calculating the resource graphs and state drift.
Typical.
They clearly needed to evolve their back-end architecture to ensure the operations didn't consume local hardware resources. What do they need?
That is the textbook use case for implementing an enhanced backend. Standard backends, like their existing setup, solve the storage and locking problems, but the computational burden remains localized.
Which melts laptops when the infrastructure scales.
Exactly. By adopting an enhanced backend like Terraform Cloud via the modern cloud block, they shift the entire execution context. The heavy lifting happens remotely on scalable servers, leaving the engineer's laptop completely free.
Okay, one more practical situation to ensure you, the listener, have the exact syntax memorized. Let's say you've been building a complex networking project locally on your laptop for a month. The code is highly polished, and your local state file perfectly matches the real-world VPCs and subnets you've spun up.
Okay.
You finally write the configuration block to point to a secure S3 bucket. To guarantee that your existing local state makes it up to S3 and isn't just silently ignored while Terraform creates a blank remote state, you absolutely must use a specific command.
You must run terraform init-migrate-state. A standard init will prepare the S3 backend but leave it empty, disconnecting your code from reality.
Which is disaster.
Absolute disaster. The dash state flag triggers the internal migration process, and you must follow the interactive prompt to type yes, so Terraform can securely map your local JSON data into the new remote vault.
Amazing. If you internalize the nuances of those three scenarios, you are in incredible shape for both the certification exam and real-world infrastructure management.
You really are.
Let's quickly recap the core mechanics we've broken down today. We established the fundamental architectural difference between standard backends, which strictly centralize state storage, and enhanced backends, which handle both the storage and the remote computational execution.
Right, and we navigated the strict initialization order of operations, explicitly avoiding the trap of placing variables inside the backend block.
Yes, very important.
And instead, securing our dynamic, top-secret credentials using partial configuration via the command line.
We also analyzed the critical flaw of local locking files in a team environment, exploring how DynamoDB acts as a centralized locking mechanism for S3. And finally, we executed the Great Migration, utilizing -migrate-state to safely transport our infrastructure's state data into a secure remote vault without dropping a single mapped attribute.
Passing the Terraform Associate certification is a fantastic career milestone, and mastering these back-end concepts will undeniably help you get there.
Absolutely.
But the true value of this knowledge lies in operational resilience. Understanding how to manage, lock, and migrate state ensures you never accidentally overwrite your production environment or create catastrophic race conditions. Mastering your backend configuration is really just mastering the underlying safety of your entire cloud infrastructure.
It is the ultimate safety net that separates a fragile project from enterprise-grade infrastructure as code. But I want to leave you with a final lingering architectural question to ponder as we wrap up this deep dive.
Oh, I like these.
We've spent this entire time talking about how to safely protect, lock, and move your state file forward to a highly secure remote vault. We've built an impenetrable fortress around this single JSON file. But what if the unthinkable happens?
Uh-oh.
What if that pristine remote state file, despite all your DynamoDB locks and S3 versioning controls, gets fundamentally corrupted, or a rogue administrator permanently deletes it from the vault entirely?
That is a scary thought.
Does Terraform have an internal mechanism to magically reconstruct its reality by reverse engineering the actual cloud resources spinning out there in AWS? Or is that single state file a catastrophic single point of failure? If the architectural blueprint burns, does your ability to control the building vanish with it? Something for you to deeply consider until next time.